Hello, in this video we're going to be talking about another kind of sequence called the geometric progression. Now a geometric progression is simply a sequence where the ratio of successive terms is constant. Now the important thing to note here is the ratio of successive terms is constant. Now you would recall that when we spoke about arithmetic progressions, we said that there was a common difference between successive terms. However, for geometric progression, what we have between successive terms is a common ratio. To understand this better, let's look at our examples that we have here. Now, for this first example, if we try to determine if this progression is an arithmetic progression, we would say 6 minus 2. Now, that's equal to 4. But 18 minus 6 is not equal to 4. 18 minus 6 is equal to 12. As you would see here, the difference between these terms are not equal. They are not constant. So this is definitely not an arithmetic progression. But what if we look at it this way? If you multiply 2 by 3, you're going to get 6. Now, what if you multiply 6 by 3? You're also going to get 18. And if you notice, if you multiply 2 by 3 here, you're going to get the next term of this progression. And that's exactly what we mean by having a common ratio. So to put it simply, in an arithmetic progression, we get the next term by adding or subtracting a constant number. In a geometric progression, on the other hand, we get the next term by multiplying or dividing by a constant term. In this case, we are multiplying by 3, which is our constant ratio that we have here. Similarly, if you look at this next example here, you would notice that the common ratio we have here is minus half. Because if you multiply 48 by minus half, you would get minus 24. And if you multiply minus 24 by minus half, you're going to get 12 because minus cancels out minus and 24 multiplied by half is 12. And you notice that we have a common ratio of minus half here. So to put this simply, for a geometric progression, we have that when you have u2 divided by u1, this is supposed to be equal to u3 divided by u2. And this is supposed to be equal to when you have un plus 1 and you divide it by un, which is the term before it, you're supposed to have a common ratio r. We denote our common ratio by r for geometric terms. And here the common ratio is 3 and the common ratio here is minus half. Now, let me get rid of this second example here so we can get more space. Now, let's denote our first term here by a like we did for our arithmetic progression. Now, to get to the second term here, all we have to do is multiply our first term 2 by the common ratio 3. Now, algebraically, that will be a, which is our first term, multiplied by r. For the third term here, we multiply 2, which is our first term, by the first common ratio here, 3, and by the second common ratio here to get us to the third term, 3. So this is a multiplied by r, which is ar squared. Now the trend continues. So our fourth term is going to be ar cubed, and our fifth term is going to be ar raised to power 4, while the sixth term is going to be ar raised to power 5. Now let's use this fourth term here to write a general formula like we did for arithmetic progression. If we have our fourth term u4 to be equal to ar raised to power 3. So if we have our un, this is going to be equal to a. You notice that here, this is our fourth term, but we're multiplying only by 3 r's, so r raised to power 3. So this is going to be r raised to power n minus 1. And this formula right here is how we get the nth term of a geometric progression. Now, on a side note here, please note that ar raised to power n minus 1, which is what we have here, is not the same as ar raised to power n minus 1. You're only raising the r to the power of n minus 1, not a multiplied by r. That is very important to note in solving questions pertaining to geometric progressions. So let's get rid of this. Now, don't forget that our un is the nth term, a is the first term, and r is the common ratio. So let's solve some examples involving geometric progressions. Our first example says, given the geometric progression 2, 4, 8 continuing, find the nth term. So our sequence is 2, 4, 8 with continuing terms here. Now here we know that our A, which is our first term, is 2. We know that our R is equal to 2 because 4 divided by 2 is 2 and 8 divided by 4 is 2 as well. Now we've been requested to find the nth term, so our n is equal to 10. Now you recall that to find the nth term, un is equal to a r raised to power n minus 1. So we have that u10 is equal to a r raised to power 10 minus 1. So our a here, u10, our a here is 2 multiplied by r, which is also equal to 2 raised to power 9. And 2 raised to power 9 is equal to 512. So our nth term, u10, is equal to 1024. Our next example says, given the geometric progression 8, 2, and half, find the sixth term. So we have our progression as 8, 2, and half, obviously continuing. And we've been told to find the sixth term. So here we have our first term to be equal to 8. We have our common ratio to be equal to, this is 2 divided by 8, which is equal to 1 over 4. And we have our n to be equal to 6 because we're looking for the sixth term. So we would recall that un is equal to a r raised to power n minus 1. So this is equal to u6 equals a is 8 multiplied by r, which is 1 over 4. And we're raising this to the power of 6 minus 1. So this is the same as 8 raised to power 8 multiplied by 1 over 4 raised to power 5. So we know that this is the same as saying 8 multiplied by 1 over 4 raised to power 5, because 1 raised to power 5 is still 1. Now 4 raised to power 5 is equal to 1024. So this is equal to 8 times 1 is equal to 8. And 4 raised to power 5 is equal to 1024. So if you cancel this out, you would get 1 divided by 128. And this is our sixth term. Our next question says, how many terms are there in the geometric progression 2, 4, 8, and so on? So we have our geometric progression as 2, 4, 8. And the final term of our geometric progression is 128, as we've been told here. We know that our final term here is 128, but we don't know how many terms are before it. So here we have that our a equals 2. We have that our common ratio r is 4 divided by 2, which is our second term divided by our first term here, so that's 2. Here we do not know n. N is what we're looking for. But we know that un is equal to 128. So you would recall un equals a r raised to power n minus 1. So here we have that our un is 128 equals a, which is 2, multiplied by our r, which is also 2, all raised to power n minus 1. So if we divide both sides by 2 here, we would have 128 divided by 2 is equal to 2n raised to power minus 1. And this is equal to 64 equals 2n minus 1. So here we're going to apply some laws of indices. We know that 64 is also equal to 2 raised to power 6. And this is equal to 2 raised to power n minus 1. Now, a sidebar here, you know that according to the law of indices, if a raised to power m is equal to a raised to power n, if the bases of our indices are the same, that means that m is equal to n. So if we apply that here, and we have a common base here, so this is also meaning that 6 is equal to n minus 1. If we move minus 1 to the other side, it becomes plus. So this is 6 plus 1 is equal to n. So our n is equal to 7. So there are 7 terms in this geometric progression, and that's our final answer. So let's talk about geometric series. As we know by now, a series is gotten by adding up the terms of a sequence. Now imagine that we have a sequence Sn, and this sequence has the terms a, which is the first term, ar, which is the second term, ar squared, which is the third term, up until AR n raised to power minus 2 and AR n raised to power minus 1, which is the final term of our sequence. Now imagine that we have a second sequence here, which is the same as Sn, only this time we are multiplying each term by our R. So A multiplied by R becomes AR. AR multiplied by R becomes AR squared. AR squared multiplied by R becomes AR cubed, until we have AR raised to power n minus 2 multiplied by R becomes AR n minus 1. And the final term here multiplied by R becomes AR raised to power n. If you're confused as to how that happens, let's just do, if we have R n raised to power minus 1 and you're multiplying it by R. Now don't forget the law of indices that says that if you have A raised to power n multiplied by A raised to power n, this is the same as saying A raised to power n plus n. So if we apply the same here, we'll have that R raised to power n minus 1 plus the 1 that we have here. So minus 1 cancels out plus 1, and we're left with R raised to power n. And that's how we have AR raised to power n here. So let me get rid of this. So now that we understand that, let's move on. Now, let's subtract Sn from Rsn. So we're subtracting the second sequence from the first sequence. Now what happens? Now you notice that AR here will subtract this to cancel out. AR squared will cancel out this. There's going to be an AR cubed here, which is going to cancel out the AR cubed here. And there's going to be an AR raised to power n minus 2 here that will cancel out this. Just like this will cancel out this. So ultimately, we're left with A here, which is the first term of our first sequence, minus AR raised to power n, which is the last term of the second sequence here. So here, let's factorize out this side. Sn is common to both terms here. So if we bring out Sn divided by Sn is 1, minus Rsn divided by Sn is equal to R. And on this side, we have A common to both sides. So if we bring out A divided by A equals 1, and AR raised to power n divided by A equals R raised to power n. So our Sn is going to be equal to, Sn is equal to A multiplied by R raised to power n divided by, if we bring this over to this side, it's going to be a division. So this is going to be 1 minus R. And this formula here is the formula for getting the series of a geometric progression. So now that we have this formula, let's use it in solving some problems relating to geometric series. Our first example here says, find the sum of the geometric progression below if there are 6 terms. So here we have that our A is equal to 2, which is our first term here. And we have that our R is equal to 6 divided by 2, which is our second term divided by our first term here, which is equal to 3. And we have that our n is equal to 6, because there are 6 terms in the sequence. So now that we have these, let's sort them into the formula here. So we have that S6 is equal to A, which is 2, into 1 minus R is 3, raised to power n, our n is 6, divided by 1 minus R, which is 3. So this is equal to 2 into 1 minus 3 raised to power 6 is equal to 729, divided by 1 minus 3 is equal to minus 2. So we have that 1 minus 729 becomes minus 728, divided by minus 2. So ultimately, 2 multiplied by minus 728 is equal to minus 1456 divided by minus 2. So minus cancels out the minus here, and 1456 divided by 2 is equal to 728. And this is our S6. So the series of the progression where there are 6 terms is equal to 728. Our next question says we should find the series for the first 5 terms of the sequence above. Now here we have that our A is equal to 8, Our r is equal to minus 4 divided by 8, which is equal to minus half. And here our n is equal to 5, because we're looking for the series of the first 5 terms. Now Sn, don't forget, is equal to a into 1 minus r raised to power n divided by 1 minus r. So here we have that S6 is equal to 8 into 1 minus, our r is minus half raised to power n, which is equal to 5, divided by 1 minus half. So here we have that x6 is equal to 8 into 1 minus. Now, minus half raised to power 5 is the same as saying minus 1 raised to power 5 divided by 2 raised to power 5. And this is equal to minus 1 over 32. Because we know that 1 raised to power 5 is equal to 1 and 2 raised to power 5 is equal to minus 32. So this is equal to minus 1 over 32. And we're dividing this by 1 minus half. So if we go ahead and solve, we'll have that 8 into minus times minus is equal to plus. So this becomes 1 plus 1 over 32. And this becomes 1 plus half. So this is 1 plus half. So if we evaluate this, we'll have that 8 is equal to, now if I'm sure you know how to evaluate fractions. If you do that, you have 33 divided by 32 for the numerator, and for the denominator you have 3 over 2. So 8 cancels out 32 here to give us 4. So we're left with 33 divided by 4, all divided by 3 over 2. And this is the same as saying 33 over 4 multiplied by 2 over 3. So 3 cancels out 33 here to give us 11. 2 cancels out 4 here to give us 2. So we're left with 11 over 2, which is the same as 5 and half. So our answer for the series of the first 5 terms of this sequence is 5 and half. Our next example says, how many terms of the geometric progression below will be needed so that the sum of the first n terms is greater than 20? And we have our geometric progression like so. Now what we're looking for in this question is the number of terms n such that Sn is greater than 20. So first let's write down what we have. We have that a, which is our first term, is equal to 1. And we have that r, which is our common ratio, is 1.1 divided by 1. And that is 1.1. Now we do not know our n, that is what we're looking for. And we know that Sn is gotten by a into 1 minus r raised to power n divided by 1 minus r. And this should be greater than 20 according to the question. So we have greater than 20 here. Now let's slot in what we have in our formula here. We have a to be 1. So 1 into 1 minus r. Our r is 1.1 raised to power n divided by 1 minus 1.1. And so this will become, if we expand our brackets here, if we multiply through by 1, we have the same thing. So we're going to have 1 minus 1.1 raised to power n, and 1 minus 1.1 is equal to minus 0.1. Don't forget that this is greater than 20, and this is also greater than 20 here. So now let's get rid of our negative denominator here by multiplying both sides by minus 0.1. If we do that, what we'll have is, if we multiply by minus 0.1 and we multiply the right side by minus 0.1. Now what happens is this cancels out our denominator here. So on the left hand side, we're left with 1 minus 1.1 raised to power n. And don't forget that in an inequality, when you multiply through by a negative number or you divide by a negative number, the sign changes. So we're going to have less than instead of greater than here. And on this side, 20 multiplied by minus 0.1 gives us minus 2. Now, we can make n historic to the formula here by moving 1 over to this side. If we move 1 over to this side, this gives us minus 1.1 raised to power n less than minus 2 minus 1. So our 1 has moved here to become minus 1. And this is minus 1.1 raised to power n less than minus 3. Now again, we can get rid of our negative sign here by multiplying through by minus 1. So if we multiply through by minus 1, we'll have that this negative cancels out this negative here, and this minus sign cancels out this minus sign here as well. And so we're left with 1.1 raised to power n. But again, because we have multiplied through by a negative sign, we're going to change our inequality back to greater than. And this is 3. So now this is our new inequality. 1.1 raised to power n is greater than 3. So how do we solve this? Well, we're going to draw on our knowledge of the laws of logarithm. If you remember, the laws of logarithm says that if you have log x raised to power n, this is the same as if you bring your power of n to the front of the logarithm here. So this is equal to n log x. So if we know this, we can use that knowledge to solve what we have here. All we have to do is find the natural logarithm of both sides, which is our ln of both sides. So ln 1.1 raised to power n is greater than the ln of 3. Now we can use this, now we can apply this rule here by bringing n to the front here. So we have that n ln of 1.1 is greater than the ln of 3. And so if we make n the surrogate of the formula here by dividing both sides by ln, or just moving this ln here, we'll have that n is greater than the ln of 3 divided by the ln of 1.1. And so if you evaluate this with your calculator, you find out that the ln of 3 is equal to 1.09861, and the ln of 1.1 is equal to 0.09531. So n is greater than 11.5267, because this divided by this is 11.5267. So which means that if n is greater than 11.2567, we have to have that n should be at least 12 terms. So we need at least 12 terms for the sum of our geometric progression to be greater than 20. So let's try that out by solving for the series of the geometric progression we have here with 12 terms and see if it is going to be greater than 20. So let's do that. If we have that our Sn, as we know, is a1 minus r raised to power n divided by 1 minus r. So Sn is equal to, our a is 1, don't forget, and we have 1 minus our r is 1.1. Now we know our n should be 12, so raised to power 12 divided by 1 minus r. Excuse me, r, we know r, so 1 minus 1.1. So now we have this to be, if we multiply through by 1, that doesn't make any difference. So we have 1 minus 1.1 raised to power 12 is equal to 3.138. And we have that 1 minus 1.1 is equal to minus 0.1. So 1 minus 3.138 is minus 2.138 divided by minus 0.1. So obviously the minus cancels out the minus here. And if you evaluate 2.138 divided by 0.1, you're going to have 21.38. So as you can see here, the sum of our sequence when we have 12 terms is definitely greater than 20. And if you evaluate for 11 terms, I can assure you that you have something less than 20. So our answer here is 12. So let's talk about the convergence of a geometric series.